to look at just the various types of redox reactions. There's lots of classes that are all classified as redox reactions. And kind of just a reminder, we've gone over acid-base, we've gone over precipitation, and basically now we're looking at redox and just the various families within redox. Okay, this is the last, or kind of when we kind of introduced what does redox look like. It was basically an equation that looks something like this, where we have magnesium plus oxygen, and we get magnesium oxide. Now this is the example from podcast 5.3, where we had magnesium going from a 0 oxidation state to a +2, and it loses 4 electrons. And then oxygen gains 4 electrons and goes from a 0 oxidation state to a 2-. So because it's going from 0 to 2-, it's reduction. And what does reduction mean? Leo says grr, so we're gaining electrons. And oxidation is going from 0 to 2. It's getting bigger, it's not being reduced. So it has to be getting bigger. So it's being oxidized and it's losing electrons. So kind of a recap from 5.3. We can get rid of our electrons, and there we go. So here's just kind of some pictorial representations of things that are being oxidized and reduced. If we were to put a piece of zinc metal in copper sulfate, it immediately turns black. And what is happening at the molecular level is something like this. Here is our zinc metal, and here's kind of some copper ions, because copper sulfate is soluble in water. There's really just a bunch of coppers floating around and a bunch of sulfates floating around. So our zinc, it goes from being part of the metal and turns into an ion, and in that process it gives off 2 electrons. So it's losing electrons, it's being reduced. At the same time, where do those electrons go? They go into what was the copper ion and turn it into copper metal. So this plating right here that we see that's kind of blackish, it is really copper metal plating out, and if it stayed in there long enough, it would kind of get that reddish copper penny color. Something similar would be over here if we put a piece of copper wire into some zinc nitrate, it looks like. We have a copper wire, and copper, because of its reducing capabilities and silver's oxidizing capabilities, copper would rather be reduced than silver being reduced. So copper goes from being copper metal into copper ion, loses 2 electrons, and silver, which was an ion, plates out and becomes silver solid. Alright, so here's kind of that first one, zinc and copper sulfate. So we can kind of break this into a couple of reactions. Or first we'll kind of look to see what in the world is being oxidized and what's reduced. So zinc, it's by itself, so it has an oxidation number of 0. Over on this side, copper is by itself, it has an oxidation number of 0. Sulfate, we know, has a -2 charge, so copper must be a +2 oxidation state on this side, and zinc must be a +2 on this side. So if we write our zinc reaction, we have zinc yields zinc ion, and we're going to add 2 electrons to this side to balance this. And likewise, or conversely, we're going to have copper with a +2 going into copper metal, and in order to balance the charges on this one, we're going to have 2 electrons on the left-hand side. So who's losing electrons, who's gaining electrons? Or if you don't want to think of it in those terms, zinc is going from a 0 to a +2, so it's getting bigger. So zinc metal is being oxidized. So we're going to say zinc is oxidized. C +2 is from a +2 to a 0 oxidation state. This hopefully you kind of have in your brain from last podcast, but there's another couple just terminology things you have to be familiar with. If zinc is oxidized, it's also true that zinc equals the Conversely, copper ion, it is being reduced, which means it is the oxidizing agent. So if we throw agent on the end of it, the agent is what is doing the reducing. Alright? So why is zinc oxidized? Or when zinc is oxidized, it means copper ion must be being reduced. So zinc is doing the reducing of copper. Again, conversely, if copper ion is being reduced, it's being reduced because it is oxidizing zinc. Okay, so again, just some terminology stuff. The way this might look would be something like this. Copper wire reacts with silver nitrate to form silver metal. What is the oxidizing agent in the reaction? Another way to read this question is, who is being reduced? Alright? Because the agent does the exact opposite of what we are really asking. So, what is the oxidizing agent in the reaction is the same as answering who is being reduced. So if we kind of look at this, and there should be a big error here, copper is 0, copper goes to a +2, silver is a +1, and it goes to a 0. Alright, so who's being reduced? Well, copper's getting bigger, it's going from a 0 to a +2, where silver is getting smaller. So, who's being reduced? We would answer that Ag ion. For silver ion, silver +1, get that a 1 if we want to, but silver +1 is being reduced. So it must be the oxidizing agent. Right, so some types of oxidation-reduction reactions. Our first one is combination reactions. They always have this form, A plus B yields C. So we have typically two elements combined to form a compound. It could be that we have an element and a compound combined to form just a bigger compound. But here's an example. Aluminum plus bromine yield aluminum bromide. Alright, and why is this an oxidation-reduction reaction? Well, aluminum starts with an oxidation state of 0 because it's an element. Bromine starts with an oxidation state of 0 because it's an element. And then aluminum ends with an oxidation state of +3 and bromine of -1. So if I were to ask who is being reduced, bromine's being reduced. Who's being oxidized? Aluminum's being oxidized. Who is the reducing agent? The reducing agent is aluminum because it's being oxidized, and bromine is the reducing agent because it's being reduced. Alright, decomposition reactions. They always have the form of C yield A and B. So again, we start with one thing and we end up with more than one thing. Here's an example. Always start with some sort of compound. If we look at this, let's see. Chlorate is a -1 charge. So oxygens are typically -2. So we're going to say this is -2. There's 3 of them. So that's a total of -6. So what -6 equals -1? Well, chlorine must be a +5. And this potassium, it's an alkali metal, so it's always a +1. I think that these are actually on the PowerPoint, so +1, +5, -2. And then on the other side, potassium is a +1, chlorine is a -1, and oxygen is a 0. So again, we can kind of look at this and see that nothing is happening to potassium. It starts as a +1, it ends as a +1. However, chlorine is going from a +5 to a -1, so it's being reduced, and oxygen is going from a -2 to a 0, so it's being oxidized. Next type is combustion reactions. Combustion is simply any time we react anything with oxygen. And some examples, sulfur plus oxygen yields sulfur dioxide. And again, we start with 2 elements, so they're both 0, 0 oxidation states, and they end as something bigger than 0 or less than 0. Another one would be magnesium and oxygen, and we've seen that one a couple times before. So combustion is any time we react anything in the presence of oxygen. Alright, the next things are going to be types of displacement, and there's 3 major types of displacement. But they are always in this general format. A plus BC yields AC plus B. So we start with an element and a compound, and we end with an element and a compound. If you remember with our precipitation reactions, it was AB plus CD yields AD plus CB, something like that, where we had a double replacement reaction. Oxidation reduction will always be single replacement of some sort. So this first one, strontium plus water yields strontium hydroxide and hydrogen. If we produce hydrogen gas, and usually this is starting with water as a reactant, this is known as hydrogen displacement. So what's happening is strontium is coming and knocking out this hydrogen, taking its place. Again, we can kind of write water is OH. There's another way to think about water. So this hydrogen leaves, and now strontium is with hydroxide. It's strontium hydroxide, and because there are two hydroxides needed because of strontium's charge, and hydroxide's charge, there'll be two hydroxides needed, which gives us our H2. Okay? So one type of displacement is hydrogen displacement. A second type, and here's the oxidation numbers, is some sort of metal displacement. Alright? Same format, magnesium comes over, it replaces titanium, and then titanium just goes off by itself, so it's an element, and magnesium replaces it. And oxidation numbers. And then our last one is halogen displacement. And again, this is a halogen instead of a metal, and chlorine replaces bromine, bromine goes off and becomes an element, and chlorine replaces bromine with potassium. Okay? The next few slides we're going to look at is how we can determine who replaces who or why. This is a table right out of your book, the activity series for metals. If you see on the left axis, the y-axis, it says reducing strength increases. So these things are more likely to be reducers. Okay? So notice that all these are starting as 0 oxidation states, and they're becoming some sort of positive value. So this first one, lithium, is going from a 0 to a +1. So it's really being oxidized, but it's a strong reducer. Okay? So the way we look at these is M is a metal, Bc is some sort of acid or water, and then B is our H2. But if we look at a problem like this, and we find calcium on our list, calcium is right here, and hydrogen is way down here. So because calcium is higher on our list, it's a stronger reducer than hydrogen is. So calcium will replace hydrogen, and we have a reaction that is a hydrogen displacement reaction. However, if we try to react platinum, if we find platinum, it is way down here, okay, and hydrogen is up here, okay. Platinum, in the presence of water, will not replace hydrogen. So this is a reaction that does not happen because platinum is not a strong enough reducer to actually reduce hydrogen. Because hydrogen is a stronger reducer, nothing happens. Notice down here we have copper, silver, gold down here. Why are these things what we make our jewelry out of? Because they don't react with water. Okay, it would be very sad if we had, I don't know, iron rings, because they would rust in the presence of oxygen. Okay, so these are called precious metals because it's what makes up our jewelry. But why do they make up our jewelry? Because they are weaker reducers than hydrogen is, and because we have so much hydrogen on Earth, usually in the presence of water, these metals are known as precious. The activity series for halogens is fairly easy. If you imagine the periodic table, you have fluorine at the top, fluorine, bromine, iodine. Again, if it's higher than something below it, it will replace it. So chlorine is above bromine, so this reaction occurs. However, if we had iodine, alright, trying to replace bromine, because iodine is at the very bottom, it is a weak reducer, so this reaction does not happen. Okay? Last one, types of oxidation-reduction reactions. Disproportionation reaction. Alright, and this, if we look at this, disproportionation is just a vocab term, just terminology you need to know. It pops up probably on the AP test, usually in the multiple choice, and probably, I would guess, once every 2 or 3 years. But if you know what it means, it's an easy point. And disproportionation is when an element, the same element in the reaction, is simultaneously oxidized and reduced. Chlorine is probably the best example given. That's our example in this case. But chlorine, is going to have an oxidation of 0. Right? Oxygen over here is going to be -2. Hydrogen is a +1. Over here, if oxygen is a -2, like it should be, and this should add up to -1, chlorine becomes a +1. And then this is chloride ion, so ion is just its charge, and then again over here we have hydrogen at +1, oxygen is -2. So notice hydrogen's a +1, hydrogen's a +1, oxygen's a -2, oxygen's a -2. So nothing is happening with oxygen and hydrogen. It's not being reduced or oxidized. However, chlorine is being oxidized, into this hypochlorite, and then chlorine is also being reduced into chloride ion. Just in your summary, classify these, just put them in order. If you want to number them 1, 2, 3, 4, but just what type would each of these fall under. If it happens to be a displacement reaction, specify whether it's hydrogen, metal, or halogen. Otherwise, it could be stuff that was covered on an earlier podcast. Otherwise, that is it, and I will see you tomorrow. Cool. Have a great night.